In this short video, we're going to look at those terms that sometimes confuse some of you. So we're going to be investigating what's the difference between error, what's the difference between precision and accuracy. In the redox titration that you carried out to determine the percentage purity of the iron ethane dioate, you titrated it against a solution of potassium manganate 7. What you had to do is calculate the mass that the technician had weighed out, and then you had to calculate the percentage error for each of the pieces of apparatus that were used in the experiment, and then use that in your evaluation. Let's get a clearer idea of those terms. Imagine you were firing shots at a target. If the shots were all over the place, we would say they would have low accuracy and low precision. So accuracy is a measure of the closeness of agreement between the result and the accepted or true value. So imagine in this target here, the centre of the target is the true value. So if all of your readings were all very, very close together, but not close to the true value, we would say they were highly precise, but they've got a low accuracy. Now imagine that they are pretty close to the true value, but they're spread about. We would say they've got high accuracy, but a low precision. If all of your readings are very close to the true value and they're all very close together, they're all concordant, we would say they've got a high accuracy and a high precision. Now, some of the wording that can be confusing is the word error. You assume you've done something wrong, but it's not. The error is the difference between your individual measurement and the true value, or the accepted or reference value of the quantity being measured. Now we can look at this in terms of glassware in a moment. So uncertainty is the estimate attached to a measurement, and that characterises the range of values. So we usually write the uncertainty as plus or minus. For example, here we've got a value of 44 plus or minus 0.4. So this plus or minus is the uncertainty. So the opposite of uncertainty is not very reliable measurement. So a high uncertainty means it's not reliable. So when we're asked about the reliability, it's how uncertain your measurement is. To credit these resources, could I direct you to knockhardy.org, where all of the sheets are available. Let's look at the glassware that was used in this experiment. The technician weighed out a fixed mass and dissolved it in 250 centimetres cubed of solution in a 250 volumetric flask. So we'll have a look at the uncertainty of a volumetric flask. If the volumetric flask increases its temperature over 20 degrees Celsius, because glass expands, it will actually then hold more than 250. So the uncertainty is only certain at 20 degrees Celsius. Now here are two pieces of glassware. These are pipettes. This pipette here has a greater uncertainty than this pipette here. This is called a grade A pipette. And again, at 20 degrees Celsius, this pipette here would deliver 100 centimetres cubed. The uncertainty of this apparatus is plus or minus 0.08. So larger glassware tends to have a higher uncertainty. This grade A pipette here, which would deliver 25 centimetres cubed at 20 degrees Celsius, has an uncertainty of plus or minus 0.03. So it depends on the pipette that you used in your experiment. The technician also used a balance to weigh out the sample of the iron 2 ethane dioate. And this is a digital piece of apparatus. So examples of digital apparatus is top pan balance or pH meter. So if we used a two-place analytical balance, the two-place analytical balance has a lower degree of precision than a three-place balance. And we'll have a look at how we calculate that uncertainty in a moment. So non-digital apparatus that we used in the experiment was a burette. And we know that the burette is read to half a division. So the second decimal place would either be recorded as a 5 or a 0. So remember, if you're reading the meniscus was exactly on the point, you would read that as 0. If the meniscus was in between two of the graduations, you would record that second decimal place as 5. To get the maximum error or uncertainty, let's take a burette, which the graduated divisions are every 0.1 centimetres cubed. What we do then is take the uncertainty as half of that division. So the uncertainty would be plus or minus 0.05 centimetres cubed. Now, since you read the burette twice, the overall maximum error or uncertainty, because you took it at the start reading, the initial reading and the end reading, you double the uncertainty. So the overall uncertainty or overall maximum error is plus or minus 0.1. Remember that the words maximum error and uncertainty are interchangeable. So let's now make the assumption that the pipette that you were using in your experiment had an uncertainty of 0.05 centimetres cubed. That's also going to be the maximum, the overall uncertainty, because you only measured out once. So how would you calculate the maximum error or the uncertainty of a 50 centimetres cubed measuring cylinder? Remember, we said it was the graduated divisions at every 1 centimetre cubed. And what we then do is take half a division of that, so that would be plus or minus 0.5 centimetres cubed. Had the two technician used a two-place analytical balance, the uncertainty would be plus or minus 0.005. So it's half a division of the last unit here, so it would be plus or minus 0.005. Had the technician used a three-place decimal balance, the uncertainty would be the fourth decimal place, which is plus or minus 0.0005 grams. Now, instead of calling these uncertainties, we're going to convert these errors to percentages. To calculate your percentage error, it's based on two factors. The first one is the maximum error or uncertainty, and then the value of your measurement. Remember, the smaller the value that you're measured, so the smaller this value here, you're going to get a greater percentage error. So in experiments where you're using larger volumes and larger masses, you're going to reduce the percentage error. Let's just take an example here. Say we have a volumetric flask which has a maximum error or an uncertainty of plus or minus 0.2 centimetres cubed. The value of the measurement is 250 centimetres cubed. The maximum error is 0.2. You divide the maximum error by the value, which is 0.2 over 250, times that by 100, and therefore we can say the percentage error for that particular volumetric flask. For your pipette, the uncertainty was 0.05 centimetres cubed. To get the percentage error, the value of the measurement was 25 centimetres cubed that you delivered to the conical flask. The uncertainty was 0.05 times by 100, and that gives us a percentage error of 0.2. For the burette, the uncertainty was plus or minus 0.5 centimetres cubed per reading, and you read it twice. So you're introducing an overall uncertainty of 0.1 centimetres cubed. So say, for example, your concordant results give an average of 26.55 centimetres cubed, then we can calculate the burette's reading. So that's for a 25 centimetres cubed delivery. Let's do it for yours. So for your burette, it's going to be the overall uncertainty, so that's 0.1. Say your average burette reading was 26.55. You then times that by 100, and that would give you a percentage error of about 0.38%. I'm rounding it up to 2 decimal places because that's the maximum value of your burette reading. So let's summarise that in your table. So pipette had an uncertainty of plus or minus 0.5, and you only used it once, so the absolute error is also 0.05. The burette had an uncertainty of 0.05. We times that by 2 because you used it twice. So the absolute error for the burette is 0.1. For the 2-place decimal balance, let's work out the percentage error. You had to calculate the mass that the technician would have weighed out, and you needed to make up a 0.03 molar solution in 250 centimetres cubed. So this is the concentration times the volume in dm cubed, and that gave you 0.0075 moles. To get the mass, you times that by the MR of the iron 2 ethane dioate dihydrate, which you should have got as 179.8, times that by the number of moles. So the technician calculated that they would have weighed out 1.34. So we're going to round that up to 2 decimal places. So we're assuming that the technician weighed out 1.35 grams on a 2 decimal place balance. So the uncertainty of our balance, because if we weighed by difference, so they would have weighed it, emptied the contents into the volumetric flask and then weighed again. So if you're weighing by difference, we're going to double that error. So that comes to 0.01 grams. This is in centimetres cubed, that is in centimetres cubed, and this is in grams. So the percentage error, therefore, is the uncertainty, which is 0.01, divided by the measurement, that was what was weighed out, which is 1.35 grams, and then we times that by 100%. The percentage error, therefore, for for the top pan balance in this case is 0.740%. Let's put that into the table. So the measurement was 1.35 grams, and the percentage error we've calculated is 0.740. The measurement for our pipette was 25 centimetres cubed, and for the burette that was your titration volume. Say, for example, a student got an average titration volume of 27.15 centimetres cubed. That came from the burette. So the percentage error for the pipette is the absolute error, which was 0.05, divided by the measurement, which was 25, times by 100. For the burette, the percentage error was 0.1, divided by the measurement, which is 27.15, times by 100. So rounding those up to 2 decimal places, the pipette gave an error of 0.2%, the burette was slightly higher with 0.37%, and the 2-place balance was 0.74. Now what we need to do to make sense of this and to use it in our evaluation, we need to add those percentage errors up. So the total percentage error is 1.31% is the total error. What do you do with the overall percentage error? What is the significance of 1.31%? Well, in the experiment you had to calculate the percentage purity, and in this experiment you actually got over 100%. And from a previous video we deduced that this was because not all of when we weighed out the iron ethane dioate dihydrate, that in fact had some of the water of crystallization over time had disappeared, we actually had more moles of the reducing agents, that was the Fe2 plus ions and the ethane dioate ions, and these were in greater amount because the water was less, and therefore we used more manganate, and therefore we got an overall percentage purity of 138%. So how reliable is that 138%? Well, we know that at 138% we can say down to apparatus error is plus or minus 1.31%. And therefore it's still over 100% pure. And we can say that the apparatus contributed to plus or minus 0.131%. So it's still over 100% impure. So again, the reason for this is because we had a higher number of moles or amount of the reducing agents, that was the Fe2 plus and the C2O4 minus. So we now use this overall percentage error to record our results. The procedural errors could have also contributed to that, but what you did to minimise procedural errors was to take only concordant results, those that were very similar in value. You rinse the apparatus with the solutions, so we can only assume that your value here is accurate to the nearest 1%.